Hello, happy Wednesday, everyone. Um, I was contacted by the McNair Scholars Program to um, invite, because I teach sophomore physics majors. Um, the McNair program is a national program that Geneseo got involved with 2 or 3 years ago, but it's a program that provides, here's a flyer for it, grad school planning, paid summer research internships, faculty mentoring, conferences, tutoring and counseling to STEM, specifically people who are first generation students, come from a low income background, or identify with a racial ethnic group that is underrepresented in graduate education. This is a pretty great program. It is you get set up with the faculty mentors, you get paid to do research, often with Geneseo faculty during the summer. And there's all sorts of cool advising and stuff that goes along with it. If you're interested, I'll probably send this flyer out to the entire group so you can peruse it at your own time. You have to apply. You have to be interested in pursuing graduate work at some level in the STEM field. Sophomores or juniors, they're particularly interested in having sophomores apply. You have to have a 3.0 GPA or higher, and it's open to all majors, including physics majors. So I think there's deadlines. They're tabling in the union. There's Zoom info sessions. I can send out the link to these if you're interested. And applications are due sort of in October through early November. So I encourage you to think about that if you are eligible. Other announcements. Exam 1 is next Friday. So far I've heard from one person who is not going to be in class taking the exam here with us. That's okay. If there are others, I just would like to know so that I can plan and schedule and do things accordingly. So if you have not yet replied to that email and you are not planning to be here in person to take that exam, please do let me know before the end of the week. There will be another sort of half homework set that gets posted on Friday that will be due Thursday of next week. So you can look for that. We will, it won't be a full homework set, although there'll be some challenging problems on there, but we'll kind of go through the things you need to do to solve most of them before we get to next week, because, or at least by Monday next week, because next Wednesday is Rejuvenation Day. And there is no classes at all next Wednesday. So we'll have classes today, Friday, next Monday, and then our next class will be the exam on Friday. I got an email about whether there will be an equation sheet. There will be an equation sheet. I will actually post that equation sheet so you can see what's going to be on it by the end of this week. So you can use it for studying this weekend if you want to. It will be 50 minutes in person. It will be written out. I will give you a packet. You will write, solve problems, or answer conceptual questions, or whatever it is. You'll hand it back in. If you're taking it virtually, you'll scan it and send it to me. Questions about how any of that's going to work? Yes. Good question. Not too many that you can't do it in 50 minutes. That's my goal. I don't want this to be a, person who does it the fastest gets the highest score kind of exam. So that will mean not a whole lot. I don't know exactly how many, but I don't want it to be a struggle for most of you to finish the exam in 50 minutes. Other questions? Okay. I'm stopping taking attendance now, although this will be our first participation class day. So leave your top hat answering devices out, because that's coming pretty quick. Isn't this exciting? We'll use it a little more regularly in the second part of the semester. Okay, where were we? We were, all this crap I have open. We were talking about the double slit. And in particular, we were talking about how the intensity on a screen after you have a double slit, how the intensity varies as the wave interferes with itself from the two slits, and constructively and destructively. And we derived the formula for this particular equation. It's weird, it involves sines instead of cosines, but that's okay. Here's a concept question for you. I'll just go ahead and do it. Let's go to it. Top hat, question number 1. Participation question number 1. The way these participation credits questions are gonna work, again, I know that there are cases where people just can't be in class in a particular time, in a particular place for whatever reason. Normally, I would just chalk that up to happenstance, and you know, you only have to get 80% throughout the whole semester to get a perfect score, and we wouldn't worry about it. This time, I will leave all of these questions open for 24 hours. So I'm not even, I guess I will answer them. I guess it's going to be kind of silly. I may have to think about how I do the grading and the point distribution for Top Hat, given the situation that we're in the semester. But I will make that announcement in the next couple of weeks if there's a change. In any event, let's just do it. If you were, so you've got a two-slit situation. The question is, if you were to increase D, the separation between the slits, how is that going to affect the pattern that you see here? Is it going to increase the amplitude? Is it going to decrease the amplitude? Is it going to make the interference fringes, the peaks, get farther apart, or is it going to make those fringes get closer together? So I will ask a quick question. How does D affect the pattern? Question mark. This is a multiple choice with 4 questions. 4 choices, go. Wonder if this is going to give. Oh, it did. That's fun. Top Hat would like to record this computer screen. That's interesting. Okay, if you can't read this number, if you're texting it in, it's 6431. Sure, why not? Later, fine. So the question is, again, increasing the separation between the slits, what is that going to do to the pattern? Increase or decrease the amplitude, increase or decrease the separation between the peaks? $15 seconds left. Even if you don't know, you should guess something at this point. I'll open it up for another 10 seconds just because I didn't give you too much of a warning. 5 seconds left. Okay, I'll open this back up after class. And if you need to redo your answer, you can do it then, which I think means that anybody can redo their answer, but I don't really know how that works. Okay, never done this before. Okay, so what is the answer? Anybody have any, I know the answer is this, and I want to shout it from the mountain top. So increasing the slit size will decrease, in making this bigger will make it closer together. Okay. Anyone want to argue any of the other options up there? You look like you're tempted. Go for it. Right, let me write this out so we remember where we were. So the intensity formula is 4I naught, oops, that's just an I naught, cosine squared, pi d over lambda sine theta. Yep. Uh-huh. So if K gets bigger, how does that affect your wave?
K gets bigger.
What happens to the wavelength if K gets bigger?
Yeah. Wait a second. Wait a second.
Right. I like your argument, but I think you argued the wrong. I think you argued the other way. I think you argued exactly was arguing up here. I like it. Anyone want to argue anything else? Two pretty convincing. So let's go through the arguments again. One is, how does increasing D affect the whole wave? This is kind of harder to pick out, but if you know how it works, if you increase a multiplicative factor inside the cosine, it makes things closer together. Interestingly, you can see this even better if you do m lambda equals d sine theta. Remember, this is the equation for finding each of those maxima points. And if D gets larger, what has to happen to the theta of the particular? Right. So we said solve this for sine theta. It's m lambda over D. It's probably even easier way to think about it. As D goes up, the angle at which the first and second and third maxima happen has to get smaller. So that's kind of counterintuitive, right? If you're going to think about this without seeing any equations, you would probably guess that increasing the slit size is going to make all those things go larger. That is not what happens. It's exactly the opposite. If you make the separation between the slits larger, it makes all those things get closer, all those fringes get closer together. They are oppositely related. Here, this isn't, this is kind of cool. This is better later on, but let me show you a cool, this is Mathematica. This is not Mathematica. That's open recent, that's the one. There it is. So we'll learn Mathematica in Math Methods next semester. You don't know it yet, but that's okay. I can still use it to do some interesting things. And my screen is so small. How do I make this bigger? If I want to zoom, that's it. Oh, that's really not what I wanted to do either. Huh. Oh, well. Oh, magnification. There we go. Boom. Ah, that's better. Yay. Okay. So Mathematica does lots of cool things. I have here a two-slit diffraction pattern. I'm set the slit width to 0 because we have so far been considering slits that are infinitely small, have no width. And I can change the slit spacing between them. I can even change the number of slits, which we'll do in a bit. But so you can see this whole thing is here. If I make the slider to the left, it'll get smaller. If I make the slider to the right, it'll get bigger. See what happens to the fringe patterns. If I make two slits closer together, they get further apart. Make the two slits farther apart, those two things get closer together. So they're oppositely related. Changing the slit spacing does the opposite to the diffraction pattern itself. Okay. All right, we'll do the rest of this stuff later. Okay, great. So, end of two-slit interference section. On to diffraction. Oh, wait. There's one more thing I wanted to do. Haha, almost forgot. This is a very cool demo. And I hope, let me stop sharing this or pause sharing. I'll just stop sharing. Okay, and I will make this really big so everybody can see it. Can everybody see this? Okay. All right, I've got two transparencies here. You can see these. These transparencies have just circles, concentric circles printed on them. And there's two of them and they're identical. Okay. The cool thing is I can put these together, and if the slits, basically this is mimicking two different slits. And I can move the slits farther apart, and you can sort of see what happens organically as I shift these around on the paper. So let's see if there's a point that I can do this where you can actually see what's going on. This would be fun if this actually works. Oh yeah, this is gonna work great. Okay, watch this. So if I move the slits apart a little bit, you'll notice some interesting things happen. You can see the two slits at the bottom here now. They're close together, but they're not touching each other anymore. And you can see what's happened. Those two sets of out spiraling circular waves are now intersecting with each other in different ways. And you can see in regions, actually where the dark pattern is, you've got, actually where the light pattern is, you've got the two waves intersecting so that they are lined up on one another. And where the dark patterns are, those are two waves where they are in fact exactly anti-aligned. And so this is exactly what you see. This is exactly the wave pattern and the two slit interference pattern that you would see in a normal wave propagated. And as I move the two slits farther apart, I want you to watch what happens to the pattern of constructively and destructively interfering waves. Watch it so you can see they're all separated by a certain amount at this point, kind of symmetrically as you go about. What happens is I increase the distance between these two slits. The spacings between those patterns get smaller and smaller and smaller. And as I move them back closer together, decreasing the size, smaller and smaller and smaller, eventually you get concentric rings. They have to basically blend together at the end. So if you want to play with these, this is actually very cool. You can, the further apart you make them, the more of these, and the closer to get these interference and constructive and destructive patterns get together. Okay, cool. Great. Okay, now back to screen sharing. And you can go away. Oops, that's not what I want to do. Okay, now on to diffraction. This, if you're following along in Holiday and Resnick and Walker, is chapter 36. Okay, so far we have been considering two slits and the interference pattern that created from two slits, but we have been considering those slits as point sources, meaning they are infinitely small. They are zero width slits. We are now going to take that restriction away and consider what would happen if we had non-infinitely narrow slits. It turns out you only need one of them, a single slit that has non-zero width. You will still get some interference happening because, again, according to Huygens principle, as the wave hits the wall where the single slit is, each of these individual wave points along that initial wave generates spherical waves that generate outwards. Those spherical waves still interfere with one another. And the expanding wave is not perfectly uniform. So that's what we're going to try to figure out now. So what are the differences between the single slit pattern and the double slit pattern? So here they are. The differences are this. So on the left, we have the interference pattern for the double slit, infinitely small. On the right, we have a single slit, not infinitely small. They look kind of similar. You get patterns of peaks and troughs and peaks and troughs and peaks and troughs. The differences are twofold. One is the magnitudes of those peaks, the amplitudes of those peaks, and the single slit are not all the same. The central peak is by far the biggest, and they go down steadily from there in terms of intensity and amplitude. The other thing is they're not perfectly evenly spaced, even in angle. That central peak is twice as wide as any of the other peaks. So things are a little bit different. And there are other differences too. So let's try to figure out what's going on here. So here's a general picture. So differences from, this is a single slit. Differences from double slit. This is single slit, non-infinitely wide. This is not infinitesimally small. This is compared to double slit, which is infinitesimally small. You get only one central peak, one double wide, so not only, one double wide central peak. And intensity of peaks falls off sharply with increasing theta. And this is not a 1/r squared effect. This is just in terms of angle. This is actually the intensity of the peaks themselves. Okay, so let's see if we can set this up. The picture now is we've got some wall, and that wall has a single slit in it, which has some non-zero width. Okay, so you've got some, again, wave propagating in this direction. It's going to hit the slit. And according to Huygens principle, what is this? Well, this is just an infinite number of smaller slits all spaced together along the actual slit itself. Huygens tells us this is just a large infinite number of slits all joined together. Okay, so let's try to do some geometry to see if we can get where the minima and maxima are. It turns out we can do one in the case of the single slit, but not the other. So let's try. Let's consider, all right, let's break this down, draw it a little bit bigger so we can actually see it. Here is our wall. Here is our make this a little cleaner. There we go. So let's say that the slit width, this is almost always called A, little a, is the width of that slit from top to bottom. D is almost always a slit separation. A is almost always a slit width. Okay, and let's consider two positions. Move these around a little bit so they're not in the way. And those two positions are one on the top and one in the middle. They are separated. So here is our first, I'll mark it in red. There's our first one, and there's our second one. This geometry could apply to any two slits that are separated by a distance a over 2, right? And there's an infinite number of them up and down the slit, all of them separated by a distance a over 2. So this is for any pairs that are two, the a or any pair that are a over 2 apart. Okay, same geometry as we had before. I'm not going to bother to draw the whole triangle, but again, we're really interested in this triangle right here. This angle is the same as this angle. And we have, this is a over 2 now, this triangle. And this is our L, our delta L here. And this is theta. And we get sine of theta. Again, this is for sine of theta is equal to delta L divided by the hypotenuse, which is a over 2. Right? The same geometry, same triangle that we did before for the double slit, it's exactly the same thing. The only difference is now instead of a distance d between those two slits, we're considering a distance a over 2. So let's do for the minima. For the minima, we know that delta L must be equal to n plus a half lambda, right? That was our condition for destructive interference. They're exactly a half a phase out of, half a wave out of phase. Where n in this case can be anything, 0, 1, 2, 3, or infinitely large. So solving this thing for, as before, we get a over 2 times sine theta. Let me not go all the way down yet, so you can still see that one. A over 2 times sine theta is equal to delta L, which is just n plus a half times wavelength. Multiply both sides by 2, we get a times sine theta is equal to, I'm going to pull the 2 inside the n term. This is 2n plus 1 times lambda, where again, n equals 0, 1, 2, et cetera, et cetera. Okay, 2n plus 1. What do we have there? What is 2n plus 1? What is the set of numbers that is 2n plus 1? It's the odd integers. 2n plus 1 is all of the odd integers. Exactly right. So that's interesting. It works the same for any 2 slit pairs that you might want to. So that's the cool thing, right? So the top and the middle interfere exactly for that wavelength, for that theta. The next two, all of them interfere. So you're going to get a full minimum up and down the entire slit. For every single slit is going to have another one that counteracts it for that particular angle. So this should be a true minimum. This should be a region where you actually have a minimum value. Works for all slit pairs separated by a over 2. Great. Are there other minima? It turns out there are. Imagine now splitting your slit up into, split the slit, that's hard to say too, into 4 or 6 or 8 or 10 different slit pair combinations. We just did 2, right? But you could imagine doing this for any even number. Instead of doing it a over 2 apart, it could be a over 4 apart, or a over 6 apart, or a over 8 apart, right? Any even number. It has to be even because you need for there to be a slit, a pair for every other slit that you've got. So that when you're going to do the interference, each of them has something to interfere with. So it only is going to work for an even number of n. So n slit pairs is not n slits. N slit pairs will translate to 2n slits. So n in this case, I'll say any number of slit pairs. I'll say this n doesn't have to be even, but 2n, the total number of slits that we are going to do does have to be that. No. So n in this case can be any integer, 1, 2, or 3, or 4, ... but not 0. You can't split your pair up into 0 slit pairs. That's not going to interfere with anything. It has to be at least 1 slit pair. Okay, so let's say we've got, let's say n equals 5. We've got 10 slit pairs. Let's see if I can do this. Again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not bad. I think that's how this works. Okay, so again, we're gonna now take adjacent slit pairs and see if we can figure out the interference, destructive interference for two slit pairs that are adjacent to one another in the diagram. Okay, remember this whole thing is A. This distance, again, we're gonna have the same triangles as we had before. They're gonna be smaller now, but that's okay. It's the same exact triangle we had before. The only difference is this side is not A over 2 anymore. What is that side? What? A over 10. In this case, n is 5, so that's 2 times n, right? So this is, so the slit width, in this case, is A over 2n. And that, therefore, we get the same, the minima occur at A over 2n sine theta equals n plus a half lambda for the minima. This is where the minima are again. Let's bring the 2n over, and again, propagate it into the little n terms. Again, well, let's just do this. A times sine theta is equal to 2n plus 1 times big N times lambda. Great. Where little n can be any integer including 0, and big N can be any integer not including 0. Okay, so what is this thing that is 2n plus 1 times big N? What set of numbers is that? Yeah, that's true. It can't be negative true. That's very true. Little n. Yeah, little n can be negative. That's true, but big N cannot. That's right. So what is the set of numbers that's 2n plus 1 times big N? The postulate is any integer not 0. Does anybody, what? Any positive non-zero or any positive non-zero integer. Anybody like that idea? Can you think of a positive non-integer 0 that you couldn't get by multiplying those two values together? You can get 1. Any little n equals 0, big N equals 1. So you're agreeing with Bailey? Yeah. I'm agreeing with Bailey too. This thing, 2n plus 1 times big N, is the set of numbers that is all positive integers, not including 0. Or negative, although those are sort of implied. So this is any integer except 0. So we can turn this, we can take 2n plus 1 times n and convert it into something that's much simpler to write. The location of the minima of the single slit occur at a sine theta equals m lambda. For m equals 1, 2, 3, not 0. This should look kind of familiar to you. What does it look like? M lambda equals a sine theta. Maybe if I said it that way and turned it around, it would look even more familiar to you. We wrote it down earlier in class. Yes, the the formula for where the maxima of the two-slit interference pattern is m lambda equals d sine theta. This is exactly the same equation with several notable exceptions. And it's easy to get this wrong and forget about this because they're talking about two different things. This is the single slit pattern. We're talking about A's at slit widths instead of D's slit separations. And this is the minima of the single slit interference pattern and not the maxima of the double slit interference pattern. It's the same formula. One refers to the maxima locations, and this one refers to the minima location. I'm going to double underline that because it's important. And the other thing is the M for the two slit pattern does include 0 because there's a nice maximum right there in the center. This one does not include 0 because there is not a minima at the center. It's a maximum at the center. Okay, so here's another concept question for you. If you got the last one wrong, maybe this is a, let's just do it. I think it's at the end. Okay, so here are 3 intensity patterns that have the same the same wavelength, light, entering both of them. Which of them has the largest slit? Which of them has A the largest? Is it A, B, or C? I'll give you a hint. This works a lot like it's the same formula that we use to calculate how the slit width in the double slit pattern affected the spacings of those things. So you got 3 choices in this particular case. Go. Uh, 0193 if you're texting with SMS is the code. A, B, or C? I'll give you a hint, it's not C. It's got to be one of the extreme ones, right? Either the one where it's extremely the widest or the one where it's extremely the closest together. So you really got a 50-50 shot at this one. So is making the slits further apart, the slit wider, going to make that interference pattern shrink or expand? M lambda equals A sine theta. 15 seconds left. 5 seconds left. Give me another 10 seconds. I'm not gonna do this every time though. Maybe that's everybody. Nope, it wasn't everybody. 3, 2, 1, it's time now. I'm shutting it down. Okay. Let's actually see what we got here now. I want to look at the, ooh, okay. So nobody chose C, good job. Vast majority of you think it's B and not A. Let's think about it. Again, the question is, if we increase A, are these slit widths getting larger or are they getting smaller, the angular size of them? So this should be, so again, M lambda equals A sine theta. Take A, solve for it. A equals M lambda over sine theta. Actually, sine theta is what we really are interested in. Let's solve for sine theta. Sine theta equals M lambda over A. That's where the minima are. That first minimum, if you make A larger, the wavelength of that first minimum has to get smaller. It works exactly the same way as the double slit pattern does. Making A larger makes those slits come closer together. It's exactly the opposite of the way you think it would be. Okay. The maxima are not as simple. Okay, so this is, let's go back to this and actually take a look at this. Look at this wavelength. Okay, so There is a question on next week's homework that involves solving for the maximum. The maximum do not occur halfway, even in angle space between the minimum, which is why it's a lot more complicated and difficult. Why is that? Well, you can kind of see why that is. They are on the double slit pattern because everything is nice and even and the peaks are exactly the same size. The peaks are not the same size. They're sort of like you're taking the pattern on the left and you're multiplying it by some function that decays steadily with increasing wavelength. And so all of those peaks are not symmetric. None of those peaks are symmetric. They all kind of lean towards the middle. And so the actual peak of I1 is a little bit to the left of the center between pi and 2 pi. And this I2 is a little bit to the left. It's a little bit closer to 2 pi than it is to 3 pi. They lean a little bit towards the central peak. We'll derive an expression for exactly where those peaks happen once we have a full description for what that pattern looks like. That's our next goal. Okay. Where am I at? 10 minutes left. Okay, our goal for this class, rest of this class, and most of Friday is to derive using phasors. This is really why we use phasors. Phasors, you don't need phasors to derive the intensity pattern for the double slit. They are extremely helpful though. There's no other really way to do it to derive the intensity pattern for the single slit. Our goal now is to not just know where those minima are. Our goal now is to derive the function that's going to give us this pattern from the geometry itself using phasors. Let's do it. Okay, so again, we're going to do something similar to what we did before, which is here's our slit. Again, this is A from top to bottom. And we're going to break that slit up into a lot of smaller slitlets. A lot of them. So break slit up. Lots of smaller slitlets. Each of them is going to have width, let's say dx, an infinitesimally small x difference. This is going to look and feel a little bit like calculus. We're not really going to be doing calculus, but it's the same sort of thing. In the limit that x gets really, really small, dx gets infinitely small, we'll have a limit of something that we can actually manage to deal with. So it's going to be similar to that in that concept. So each one of these has width dx. Okay, so what we're interested in doing now is to construct so again, each one of these is going to be contributing a spherical wave according to Huygens principle. Each one of them, if we take some point on the screen, is going to be, that intensity of that point is going to be impacted equally by each one of these slitlets, right? And so each one of them is going to be contributing a tiny little phasor to the total intensity of the slit on the screen that we're going to be adding. Okay, so we're going to need to consider the phasor of every single one of these, potentially infinitely many phasors up and down the slit. Okay, so we're going to break, each will have, the geometry is still the same. We've got some, let me see if I can move these words down here. This is one of the cool, I can't do this on a regular board if I mess up. Again, we're thinking about some slit point that's way over here on some screen. And we're thinking about the geometry of each one of these individual little wavelets and the contribution that each one of them is going to have to the intensity of that final point. And each one of them is going to have a slightly different phasor. Now, the intensity from each one of these should be the same. So the amplitude, the length of each of those phasors should be exactly the same, right? So that makes it a little bit simpler. Each slit will contribute a phasor at the screen. Let's say it's point P. All of those phasors will have the same intensity and therefore will have the same length. What is so the phasor for each slitlet is going to be we know that the total length is going to be the same, but there will be a slight phase shift difference between each of those phasors. They'll have slightly different path lengths. We'll have slightly different path lengths. And therefore have slightly different phase angles. So what is the phasor for each slit going to look like? Again, let's draw the triangle, this exact same triangle that we've drawn in every single other case that we've been thinking of. The only difference now is that here is dl. Instead of an A or a D here, you've got a dx, right? Because we've split each one of those phasors, each one of those slitlets into a dx. So this is still our theta value. So we still have sine theta is equal to delta L over dx, exactly the same as we've done this every other time. Solve this for delta L is dx times sine theta. So what is the difference in angle? Remember, this is the difference in phase between the top one slitlet and between adjacent slitlets. We define this to be 2 pi to give it an angle times delta L over lambda. That's the phase difference, the phasor angle between adjacent slitlets. And we know that that has to be, we know what delta L is, so we can just plug that in, and this becomes 2 pi over lambda times dx times sine theta. Yeah. We're not going to end up taking an integral. It seems like that's where we're heading, but we're doing something geometric instead. But that's a good idea. It looks like we're heading towards taking an integral, but we're actually not heading towards taking an integral. Okay, this is exactly the same before, except dx is very small and we have a lot of them. What do these things look like? Well, if we were to line, again, we're interested in the phasor, right? We got a bunch of phasors. Yeah. The 2 pi comes, again, delta L over lambda is the total, like if delta L over lambda were 1, you'd have a perfectly one phase off. We'd be perfectly one phase off. The 2 pi turns it into a radian angle. Right? It's just anglifying the delta, so the integer, delta L over lambda gives you an integer number of wavelengths that you're off. 2 pi turns it into an angle. Yep, that's all it does. So what does this look like? Let's draw the phasor diagram. What do phasors look like? They look like this. Here's U and V. Let's say the first one is at 0. The second one is going to be exactly the same length, except it's going to have some phase difference, delta phi. What's the next one on top of that one going to look like? It's going to be exactly the same length, except it's going to be different from its neighbor by delta phi. And the next one after that's going to be the same length, except it's going to have some difference delta phi. As you make dx smaller and smaller, those d phi's are going to get smaller and smaller. They get closer together, but also the magnitudes of all those phasors are going to get smaller and smaller too. What is it going to look like if we pile all these up? I'm out of time, but I want you to think about that. If we have an input, again, if you make the dx value smaller and smaller, two things are going to happen. The amplitude of all of those is going to get smaller, and the delta phi is going to get smaller and smaller. What's going to happen if you start adding up all of those individual phasors? What pattern is it going to look like? It's going to start looking more and more like a circle. That's exactly right. So we'll explore that geometry and see how we can use that geometry to determine what the intensity is at the screen on Friday. Sorry?
I sliced my finger open in lab.
Oh no, how'd you do that?
When I say sliced it open, I mean like it looks like a paper cut, but I was bleeding everywhere.
Oh no, how'd you manage that?
So we were doing the Diffraction interferometer.
Yep. Experiment.
Experiment, yeah. And one of the movable mirrors, it wasn't screwing down all the way. And I was like, oh, what's going on? And there was this washer underneath, and Dr. Marcus was like, oh yeah, you just gotta thread it back up. So I went like this on it, and the washer sliced my finger open.
Wow.
Yeah, and I was
Who knew that physics lab could be dangerous?
it didn't even hurt.
Yeah.
It's the weird thing. So I was like, oh.
You're just bleeding
everywhere, sir.
What happened?
Yep. Bailey sliced her finger open a little bit in lab yesterday on one of the washers.
I hope she's doing okay.
She does seem to be fine. It looks like a paper cut now, but apparently there's a lot of blood yesterday.